level is one of the very important parameter which is used in any nuclear any radiation detector. So if you want to publish a paper on your measurement, you should always report what is the minimum MDL or MDA of your detection system. So reviewer will always ask what is that, and you should also be knowing what is the background of your detector, because these are the important parameters, as I said in the beginning of the session and the previous practical session. So what is the important parameter is MDA, and this what we use is IAEA formula. So International Atomic Energy Agency has given, of course this is derived from basic statistics. You can get it from any statistic book also, and nowadays across the world, so in majority of the laboratories which does this environmental radioactivity measurement, they use this formula. MDA is equal to 4.65 into root B. B, what is B? B is the background of the detector. So suppose if you are using the high purity gamma spectrum, you should take the background in the under that peak. For example, I'll tell you the peak, there is a peak of 609, bismuth 214. You know which region of interest, number of channels you have used, starting channel, ending channel. And for the same region, you should note down the background. And this of course, to subtract from the sample spectrum. So that into efficiency, A, abundance, counting time, and weight of the sample. So you should always report the minimum detection level of my detector for a sample mass of 250 gram is this much, or a sample mass of 100 gram, or a sample mass of 5 gram. You should report what is the MDA, and this is how you calculate. So those who have not calculated it yet, and this is applicable for all the nuclear detectors, okay, be it alpha spectrometer, be it high purity germanium detector, sodium iodide detector, or zinc sulfide detector, or the liquid scintillation spectrometer which is used by ARIA, everywhere, okay, for all this detector is the same. So this is the formula you use. So in yesterday's and day before's experiment, you have learned how to evaluate the gamma ray spectra, how to take the counts, how to subtract the background, and how to calculate the activity. Now today what we will do is, those who want to know, yesterday we have put some sample alpha spectrometer, this alpha source or alpha radiochemical separated polonium-210 plated silver disc onto the alpha spectrometer. So it is there inside the alpha spectrometer. Now the spectrum is acquired. Those who want to see the spectrum again, you can go there and note down the counts and calculate the activity again. And today afternoon you have two tasks. You go to the sodium iodide detector today and find out, adjacent to the high purity germanium detector there is a sodium iodide detector. So you see the spectrum of the both the spectrum. So what Avanish will do is he will show the HPG spectrum and he will show the sodium iodide spectrum live acquiring using a uranium-230 or thorium-230 to source. Let it acquire, or you can show them the cesium or cobalt source. So this anything is okay. Cesium source you put, it will be very fast. You should appreciate that what is the resolution, what you mean by resolution, how the sodium iodide spectrum looks like, and thing. And then for evaluation of the activity of the sodium iodide detector, the activity formula remains same. Only thing is how you evaluate the spectra. So there are, since we use advanced Genie software, this software also gives you the Compton suppressed, Compton corrected counts, that is area, integral and area. It is a highly advanced spectrometer. What you are doing, you have done yesterday, day before yesterday. The spectrum, the software is able to do it automatically. So you create a batch file. So if you create a batch file, it will start counting at a particular time the time you set. For example, today 10 o'clock you want the spectrometer to be counting the sample, start counting. So you can create a batch file. It will start at 10 o'clock. It will count next 24 hours, 48 hours, whatever you set. Then it will evaluate the entire spectrum. It will correct the background. It will search the peak. It will do the, if you feed the mass of the sample taken for analysis, it will give the final activity. So many becquerel per kg it will give. So it is so highly advanced software. But then why we have asked you to do, because all of you may not have the same software. So you want to do it yourself after you go back to the lab. So that was our objective. If you want to see that option also, we can probably try to do it tomorrow afternoon. How we do it automatically with the advanced software. It is up to you. And today what we do, we are giving you a set of samples, okay, which are in different geometry. We have recently received a set of sample from IAEA for intercomparison, international intercomparison. So we already finished this assignment. We submitted the data and all our data was accepted through. So what we do, we give the same sample to you. We know what is the activity of individual radionuclides in this. And we have standard reference materials also for this in the same geometry. Adu kuda illi untu. Reference idradu standard kotidradu. This is standard, this is standard, this is sample. So this again contains very low activity. So if you start counting today, it will finish tomorrow. So why we give for this reference material, we give you already stored spectrum. And for the sample, either we can give the already stored spectrum, or you can put it for counting today and get the counts tomorrow. It is up to you, as you wish. But it is already counted, but you should evaluate the activity for both the samples. This as the reference, this as the unknown sample. Take this as an unknown sample. You can give the reference spectra with this, and you put this as a sample. Let it count. Okay, you see the counting, how slow it is, how fast it is. And meanwhile, you take the already stored spectra for this. Do the activity calculation. And at the end of the day, let us find out whether you have evaluated it correctly, whether you are getting the target value. Okay? And tomorrow morning you come back. By that time, this will be the data, new set of data will be ready. Spectrum will be ready. You do it again if you want. So that is the one objective. And second is, we have a set of filter papers.
One is blank, one is standard, one is cesium,
Yeah.
one is stone shaft.
Yeah. One is standard.
This is blank.
Yeah. We have a set of filter paper. One is blank, which is expected to have zero activity, background. And we have another filter paper with the reference, where the activity is already spiked. And we have one unknown. Okay. This also you can put it to counting in another detector. Meanwhile, this reference standard reference material sample spectra also we will give you, and you take the other one, evaluate the activity. Okay. And we have another set of,
This is for small geometry.
yeah,
Thorium and uranium.
yeah. So we have been talking about different types of geometries. So you can see that we use reference material in various geometries. Spectra are available for these also. So you can recall this from the computer, and if you wish, you want to calculate. You can also, for example, you take 250 gram of as the reference material, and this is the unknown, and you evaluate, and you will find that for the geometry which you have used for 250 gram, if you use that as the reference spectra, and against that if you evaluate the activity for this, you will find that it will be off. Okay. So you can do all these things whichever way you want. So I recommend that first you finish this assignment. You can split yourself into two groups. One group, let them do this water sample. Other group, you do for filter paper. And tomorrow you can reverse it. Okay. And if you, and meanwhile, we have prepared one polonium sample plated onto the silver disc without tracer. Is it not, Arya? Yes. Without tracer. That is also ready. If any of you want to see the gross counting technique, gross alpha counting technique, so that you can take that sample, take it to the gross alpha counting system, put it and count. That also you can find out. You can find the efficiency of that. You can, because the activity is known, and you can play with that gross alpha counting technique. That is also possible. So target is one batch should finish this, other batch should finish this. Over and above, if you have interest, go to the alpha spectrometer, note down the counts again. Go to the bulk gross counting system for polonium and check that one also, right? Any doubt? Any clarifications? Okay? Clear? My friend from Manipal is in a deep thought.
I think I have a friendly guide here.
You are?
A friendly guide here.
Okay.
He is much better in the subject.
Okay, oh, I see.
Back page.
So,
He's
you,
scribbling down very basic.
so you feel you are safe. He is scribbling down, so you will join him, you are safe. Okay. Any input is required from our side? No. Then Avanish, give them one batch, let you go to you take this water sample and count, but be careful. Be careful not to ensure that it doesn't fall down, because in case it falls down, everything will be contaminated. So in all the low background counting laboratory, utmost care has to be taken to avoid contamination. Okay, even a drop of sample, maybe it is background sample, still you do not know. Utmost care has to be taken to ensure that there is no spillage. Okay, that is one thing, right?
By the time I will finish basic explanation of sodium iodide and HPG, and then we can start counting. By the time the second batch comes, we can do around like that. 1 minute, I will inform the same. ಇವರಿಗೆ ಇದು ಇನ್ನಲ್ತ ಸ್ಪೆಕ್ಟ್ರಮ್ ಕಾಣಿಕೆ ಇನ್ನಲ್ಲಿ ಇವರ ಪ್ಲೇಟ್ ചെയ്ത സ്പെക്ട്രം ഇല്ലേ അതിൻ്റെ കൗണ്ട് എടുത്ത് വരട്ടെ അപ്പോൾ ആകുമ്പോൾ ഞാൻ ഇവർക്ക് ഒരു ബാച്ച് സെറ്റാക്കിയിട്ട് വെക്കാം 2A 2B 2A 2B 2A ഓപ്പൺ ആക്കട്ടെ 2B ഓപ്പൺ 2B ഓപ്പൺ ಬರುತ್ತೆ ഇവിടെ spectrum is developed, so you can take this counts. Okay? 6. Yeah. So I have showed it in the first day. So even then, I can show you a cesium spectrum at the later stage. We can develop it right now if you want, or I can do it later also. So let us start with that. Yeah, just give me a cesium sample. So I'll keep all the 3 together. So let us see.
3 together?
Like 2 together. Cesium and cobalt. Yep. So let us see how.
More than the 4 because the coincidence will also occur.
One నిమిషం.
It's a flat surface.
Yeah, it is a well type detector. I had shown you, no? So I've kept. I will show you later. Okay, so I've kept the source carefully. I have to close it. It's very heavy. It's lead. Okay. So now what I will do is I'll just show you the spectrum first. Yeah. Okay.
Is that gap in the lead seeding doesn't make any problem in the counting.
Not much, because we correct for background, no? Actually, it was not there, but
Because then the K40 in background will be much greater.
I understand. Actually, what happened, there is just a small gap between the things, so we are trying to fix it. Is the medium communicating or not? You have to check. Medium is communicating. It's on. Medium service manager is on. Switch it off. So it's not responding. So I'll just no, so I'll have to restart it. Yep. So just restart. So actually there is something called as VDM. So that has to communicate. That is the communication link between the your MCA and the setup and to the PC. So if
Then the medium problem is again.
yeah, medium. No, it is only with this analog. The digital systems are very much seamless.
MCA what, how much?
This one is 30, I think 16K. It is 16K.
And the other one?
This is 32K. All others are 16, this is 32.
32.
So we'll just wait for the system to on. So first I will just prepare the sample. This, how do you want to do it? Do you want to count the sample yourself and take the results tomorrow, or is it okay you can, if I give you the counted spectrum? Because it's again, it's the same thing. It takes a long time, so this doesn't have much activity. So I will show you what exactly these samples, how do we get it. So this is the basically the sample that IAA gives us. So what they do is that they don't tell anything. They just give the values of standards. Okay, the standard, where is no, nobody's there, so I'll find it out. So you have, they'll give the value of this sample too. They will give value of one swipe sample which has the activity, and then they don't tell us anything. So they will say that you have to analyze and you have to give us the results. So before keeping it in, I have to ensure that it does not spill. Correct? Give me that IAEA report 2024. So let us just make sure that it does not spill. Okay. So this one works. If you want, you can just remove the air from this, and now your sample should look something like this. So what if there is some leak here, it should get contained here. So I'll show you the report how it comes. So this is a sample, the paper that they mail us. So you can see that they have sent us instruction to participants. So you have spiked water, this is QC, meaning quality control. Then you have sediment bauxite that I am not giving you right now. Then you can see 4 spike samples, in which 5, sample number 5 over here, sample 5 over here is our sample that we have to analyze. Sample 6 is QC, quality control sample for cesium-137. Sample 7 is QC for strontium-90, that we cannot do by gamma spectrometry, we have to go to beta spectrum, so we will avoid it. And sample 8 is a blank. However, that's already explained to you. So the sample 1 and 2, they will give sample preparation, how they have done it. And you can see that radionuclide content in water too. Americium, barium, cobalt, cesium, tritium and strontium. So in this, whichever is applicable to us, we have to take, they have given the activity concentration in becquerel per kg, and they have given us a reference date. So the reference date over here is 2024-11. So from here, from the counting date, we have to back calculate and find out the activity on, from that date to calculated date, we have to calculate the activity, and then we have to calculate it. And sediment 3-4 is not applicable for us. So sediment samples 5, 6, 7, 8. They have given a cesium 137 activity, and 7 is not applicable in this tree because it is strontium 90, can't be analyzed here. So these are the only thing. Then they will give a end date and some related informations on the sample, the requested reports per sample in what on what units they require. Say they have said becquerel per kg for most of this. Sample 5, it is becquerel per sample. So that's it. So these are all evaluation matrices. How they evaluated, and if it is A, it means accepted. Trueness and precision is accepted. N means not accepted. W means trueness is accepted but precision is not accepted, so it would be warning, so you have to correct. So we have got all almost all as accepted, so most of them are as accepted, so not most, I think all. So that's how we can say that our results are standard. Okay. ಸ್ವಲ್ಪ ಕಡಿಮೆ ಮಾಡಿ second. So that's all about it. So I'll just show you a spectra before starting with the counting of the sample. So
This gamma equation.
yes,
Gamma acquisition.
yeah, we have renamed this title as such. Okay, now what?
5.
Yes,
Open data source.
yeah,
Detector.
yes, and
Now select the detector. There is
Now
only one.
it's detected.
yes,
Then click open.
open. So the detector is open now. Detector should come. Okay. So this is a spectrum that I had kept for which one? I don't know. Just find out what spectrum is this.
So there is it is K40.
1446, the K40.
It is
It is K40. Okay. So I'll save this spectrum. Save as okay. Save it as RGK. Okay. So now I've saved the spectrum. Now you have to analyze a spectrum. So how do you do that?
We have to open the spectrum file.
It is spectrum and that is already open.
ROI we have to.
No, I have to start calculating. So what should I do?
First you want to select the display.
Acquire setup. Okay.
Time.
Time. Yeah.
You have to change it.
Okay. How much you want to give? This is a high active sample, so we'll give
10,000.
100.
100
100
seconds.
is enough. Okay. Next, what will you do?
Then MC first channel we have to select.
No.
No, just start.
Start
Acquire
only,
it. Just click start in the
Start.
acquire.
Start.
No. No. No.
Data source is there. High.
Everything is set.
Set.
High voltage we not to
Time
change.
is set.
There is one thing you have to do. Just
Take that.
Clear the spectrum.
Clear.
yeah.
Clear the spectrum.
Clear the
These things we have to clear.
There is in acquire.
Clear.
clear data.
This one.
Yes.
Clear data. And ROI.
Yes.
Oh yes.
If
Everything.
you click clear,
Because that is old data. Now you want new data. So you don't want old data to add. Now start.
So start.
Start.
So the now new peak, new
Yeah.
spectrum will come.
Yeah. Start. See. So that is okay. You have seen how narrow the channels for cesium was already, right? So you can see that here, this is what? Wait. This is 661, correct? Yeah, 661. So it is cesium. Can you see the channels over here? This is the control R. So you see the channels. So this channel, this energy over here is what? 785. And this energy over here to the other end of the spectrum is 552. So between that, if you get any other peak, it will merge with the peak. See these two peaks, you remember how it was shown in HPG, don't you? It was very spacious, very well distinguished. Now look at this. It is 1180 and 1332. It's all nearby, very close, like only one channel is separating both of them. So counts from this can spill over to this, counts from this can spill over to that. So that resolution is less. So that is why we prefer HPG. So this point I think it is very clear now. So we don't have to worry much about it. Yes? So here we have kept both the peaks, both the sources, cesium-137 and cobalt-60. So you can see all three peaks and also a coincidence peak of cobalt. Okay?
That is this one, no?
I hope this much is clear. Yeah, you can see Compton peaks, backscattering peak. Yeah, every X-ray peaks I don't think so. X-ray peaks is not there.
They won't get that.
Yeah.
It's low energy.
Low
It
energy,
after
yeah.
600
Yes,
kV.
yes, correct.
So yeah, X-ray peaks are not there. So I hope this much is clear. Now we will start with the task for the day. So I will give you,
In what cases then we go for sodium iodide detector?
if you want quick results, if you want
Only identification if you want, then this is the
Pardon?
that peak.
only identification. For example, if you want to find out what is there.
What is this?
So if you want to check
Quick
if there is
identification of,
cobalt, if there is cesium, if there is, or also sometimes we do calculation also in this, like most of us, because this is quite expensive. As Roy sir told, they are paying around 100,000 euros. It's almost like 10 crores or something like that for this HPG system. It is in Finland, but here it might be around 1 crore or something like more than 1 crore. More than 1 crore for this system. So it's not affordable for every laboratory to have it. So in that case, sodium iodide results from sodium iodide or also standard calibrated sodium iodide is acceptable. But the standard deviation would be very high, correct? Well, how much standard deviation you give? Plus or minus 100 becquerel? Like 100 plus or minus 10%. Yeah, 10%, 15%. Here we are standard deviation is pretty low, less than 5%. Okay. So MDA formula you already know. Yeah, I had already explained. So using the background that you have already taken, you can calculate MDA. Okay. Yeah.
Calculating MDA.
Okay.
Each element I calculate.
Yesterday you have gave the counting time of background as 60,000 seconds.
Yes.
And for sample it is 30,000.
Yes.
And what should we take as T? 60 or 30?
In that case, MDA should be calculated according to your sample time. Sample, yeah. So MDA, while we are calculating, we say that MDA is so much. Yes. MDA is so much. For so much, I had explained it clearly that it is for so much seconds. So we are saying for this much seconds and this much weight. That information should be clearly mentioned. Okay.
That is why we should take the sample count and background count at the same time.
Yeah, maybe that is also done. Or else I can take MDA background by half.
Okay.
So background, so yeah, it is nothing but for 30,000 seconds.
Should not be linear all the time. That half value.
Approximately half,
Yes, approximately.
maybe 1 point or 2 point here and there. Does it matter? No. Okay, so we will start with the experiment. So for this batch, whether you want water sample or do you want swipe? Water sample. Okay. So if you want water sample, we will do it in this lab, this PC, and swipe samples we can do it in that PC. Okay, the data sheet that have been given to you right now contains some radionuclides. Okay, those radionuclides might be or might not be present in the sample. Okay, so first what you do is, first I'll give you QC sample, water sample. In that you identify the radionuclides and write it down in this table, and after identification write down the abundance, all those data, and write down the counts, calculate the efficiency. That whole activity might take today till evening. Okay, yeah. So next, tomorrow you can do the calibration, like activity identification. Okay, is that fine? Okay, so you can also, by doing this exercise, you can also compare the efficiency that you have got yesterday and efficiency that you are getting today, and you can compare them, like how different it is. It is widely different. So that is why all these things what we have said, geometry is always important. Also, in yesterday's class, 3 different batches did efficiency in 3 different detectors, correct? And detector efficiency between 3 detectors is quite different, correct? So you might have observed that also. But if another batch has also done in these 3 different detectors, so you and the the guy who has done in the same detector should get similar values. So that also you can check. Okay. Now I will give you. I will check whether first I will give you the water samples here. If the other batch is not coming today, I will give you water samples in that sample. So I will divide you into 2. If the other batch is also coming today, then what we will do is that I will keep that as reserve for them. I'll ask them to calculate efficiency in that. Okay, that would be much better. Okay, so you can have your chairs around here. So do you want me to count these water sample and show you the spectrum live counting? Do you require that? Okay. So then I will keep the sample inside. Is that fine? Okay. Okay. Because I don't know. It is very sensitive. Okay. So this is sample to QC water. Now I have put a plastic, right? Yeah. Plastic ಒಳಗಡೆ ಏನಾದರೂ ಡಸ್ಟ್ ಇದ್ರೆ it will again affect. Plastic ಹೊರಗಡೆ ಡಸ್ಟ್ ಇದ್ರೂ it will affect. But this is a fresh plastic. Okay. So that is what I said. You always assume the sample is dusty. Always assume sample is dusty. Okay. So I'll just remove the air little bit. ಮೇಲ್ಗಡೆ ನೀಡು. Exactly.
Tissue ಇದಕ್ಕೆ tissue ಇಟ್ಟು
ಅದು just our precautions so that we don't contaminate the detector. ಅದರ ಮೇಲೆ ಒಂದು ಕವರ್ ಇದೆ, ಅದರ ಮೇಲೆ ಟಿಶ್ಯೂ ಇದೆ, ಡಿಟೆಕ್ಟರ್ಗೆ ಸಪರೇಟ್ ಕವರಿಂಗ್ಸ್ ಇದೆ. But we are being extra cautious. Not just, see, you might think that we are being over cautious, but if there is even a smallest leak, the whole setup has to be.
One more. When we are taking the background, you are keeping that thing in on? No.
See, there are 2 types of backgrounds you can take. We keep empty detector. We don't keep anything.
Okay.
We don't keep the bottle. Otherwise, you can also keep the bottle to subtract the background that is coming from the bottle, from your container. That also is acceptable.
These bottles are glass bottles.
No, plastic.
Then it is fine, but because if you use glass bottles,
Glass, then
K40,
yes.
K40 is
Not only K40, I think some glass bottles, or the older ones, can have traces of uranium. So silicon, and some silicon may contain thorium. So those issues are there. So plastic, it's not a big issue. So now let me open.
You want the chair?
No, it's fine. So I'll start counting. Okay. So same thing, whatever you did right now. You want to do? Anyone?
Yes, sir.
Yeah. So the same thing you repeat?
Okay, first we want to clear all this thing.
Yeah. There is clear here.
Clear here only.
Yeah. And start.
time set.
Start only.
1 minute. Time set is wrong.
MCA.
Require. We will do it for, I think, 10,000. It is not enough, but
10,000.
we will do it. Yep.
Start appearing.
Yeah, see, this counting is pretty slow. Still, there is no peak that is being developed. So, I think it will take at least, 2 hours. We have counted, I think, 60,000 seconds. 60,000. So you can see why we are giving you the already counted samples. So now I will open the file, compare. Yes, so display, clear, ROS, clear all. So all the background, everything I have cleared. I've counted, the sample is counted for 60,000 seconds. It's up to you. Okay.
No, and background, like backside that is going on after counting.
Yeah, counting is going on.
Going on.
We can even shut down the PC and go home even the counting is going on. It will not affect the. Yeah.
It will, when you switch.
See, suppose so now it is counting is over here. Okay, I'll close. No, I have not stopped it. So here you can see that it is still acquiring. Acquire light is on. Okay, so that means even if I shut down, there is no effect to the detector counting
How
system.
do you open that one then?
Same way. It is just like how, see, it is something like there is already something playing on in your TV channel and you are just switching on that channel. So when I switch on that channel, I'll get this, whatever is happening over there. The program whichever is being run.
You don't have to give start or something.
No. It is background, it will be, unless I stop it, there is no problem. So display.
This is previously analyzed one.
Yes. So it's, the floor is for you.
Gamma lines used based on that. We are supposed to
Energy control.
So for your reference, I'll just. ಅಲ್ಲಿ ಮೇಲೆ ಆಯ್ತಾ ನನಗೊಂದು ಒಂದೇ ಒಂದು ಕಾಪಿ ಬರುತ್ತೆ ಆಯ್ತು ತಗೊಳ್ಳಿ
See, if you place the cursor at the peak, that will give you the energy. That is the importance of energy calibration. Place the cursor at the peak. It will give the energy. Then you look at the data. This energy corresponds to which one? That's why we wanted you to do the calculation. So what is the energy purpose of energy calculation? If a unknown energy, if there is a unknown radionuclide is there, by measuring its energy, you can identify which isotope.
Sir, should we consider it as a peak? Sir, should we consider it as a peak? Should we consider it as a peak?
No, that is the Compton continuum for the one.
No, that is 49.
No. You take only very prominent peak. Yeah, that is a good peak.
This one 59.6.
Huh?
Ratio.
Which one?
59.6.
Yes, yeah.
So note.
If it's not there, you write down.
You can note. You can note.
Just note down the energy.
It's almost
No, it has a gamma also. Go on and
We need to check everything. The book.
We need that count also. Yes, we will have.
No, you do one thing. You find out the peaks that are present, and using LARA, you find out which peak it is there, and then I will give you what is the activity of that peak. Okay.
So first identify which are all the isotopes present. Okay. Go to the, take the cursor to each peak, identify the isotopes.
ಸರ್ ಆಚೆ ಬೇಕು ಚೆನ್ನಾಗಿ ಬರ್ಲಿಕ್ಕೆ ಹೇಳೋದು, ಆಚೆ ಬೇಕು ಚೆನ್ನಾಗಿ ಬರ್ಲಿಕ್ಕೆ ಹೇಳೋದು,
ಅದು ಅವರಲ್ಲಿ ಹೋಗಿದ್ದಾರೆ
ಮೇಲೆ
ಯಾಕೆ?
ಗ್ರಾಸ್ ಕೌಂಟಿಂಗಿಗೆ.
ಅವ್ರು ಮುಗಿಸಿ ಬರಲಿ.
ಅಲ್ಲ, ಇದು 2 ದಿವಸ ತಗೊಳ್ಬೋದು ಸರ್. ಒಂದು ದಿವಸ ಎಫಿಷಿಯನ್ಸಿಗೆ, ಒಂದು ದಿವಸ ಆ್ಯಕ್ಟಿವಿಟಿಗೆ. ಅವ್ರಿಗೆ ಇವತ್ತು ಬರೋದು, ನಾಳೆ ಬರೋದಿದ್ರೆ ಕಷ್ಟ ಆಗ್ಬೋದು.
ನಾಳೆ ಬರ್ತಾರಲ್ಲ.
ಅಲ್ಲ, ಇವತ್ತು ಬಂದು ಎಫಿಷಿಯನ್ಸಿ ತಗೊಂಡೋದ್ರೆ ನಾಳೆ ಅವರಿಗೆ ಆ್ಯಕ್ಟಿವಿಟಿ ಕ್ಯಾಲ್ಕುಲೇಟ್. 5 ಸ್ಯಾಂಪಲಲ್ಲಿ ಕಷ್ಟ ಇಲ್ಲ, 5 ಸ್ಯಾಂಪಲ್ ರಫ್ ಆಗ್ತದೆ. ಇದು ಸ್ವಲ್ಪ ಕಷ್ಟ ಉಂಟು. ಆಯ್ಕೆ
If you do just efficient concept, you might not understand the nuances in calculation. One batch is counting the gross, or this is the gross of the detector. They calculate the background, then they calculate the activity. How much are you using of a mixed radionuclide source.
Start from here.
ಬೇರೆ ಮಾತಾಡಿದ್ರೆ ಆಯ್ತು ಇಲ್ಲ
Can you start from here? Okay. Controller.
Control. Yeah. This is controller.
Where is control?
it may not be
Controller. Same line it should be.
If we talk of barium 133, if it is there for 356, so it is expected 302 also will be there, no? Maybe everything.
5 elements are barium. 5 elements are barium.
Yes, once it is there, we should see individual evidence.
Also variant. That's the 302.
Yeah, see, it is there.
Not many,
It is fine.
You see the individual abundances, you will understand it. Individual isotope చూడండి abundances ఎలా ఉన్నాయి. For barium 133, what are the abundances?
So 1, 2, 3, 4, 5. 5 radionuclides from barium 133.
A value. C value.
There are how much abundances we are getting individually. Barium is that's it. 33.3.
Then for 276.3, that is 7.13. Does that M play a role or beta stable? It has to be met, then you cannot take this one.
More meaningless. അടുത്ത സെഷൻ പിന്നെ വീണ്ടും അവിടെ 60 സെക്കൻഡ്
No need actually, because first of all the counting time itself is very high. 1 or 2 counts
Down as 18.
15 instead of
15 note down as 18.
but actually since the counting time is very high, it doesn't matter any change. 3-4 counts.
But these are okay. You also don't have to correct the activity values because half-life is so much higher, more than year, 1 year.
This is for
302.
7.
302 how much?
7.
355 next.
Yeah, I will.
350.
Let's see.
Less. Automatic count. Yeah,
less than
Yeah.
15.
15. Next to 15.
1.5, ma'am.
1.5.
Myself. No,
383. 18. 180.
Okay.
18.
because equilibrium is not guaranteed.
661. Then what? 610. 1173. 19. 19.
So they have taken the activity, all that exercise is done right now, right? So yesterday we have seen spectrum of cesium and cobalt in the day before yesterday, or yesterday, I guess.
It was not for stable, it was for late.
HPG, yes.
HPG he showed, na?
Yeah,
Cesium
I just
spectrum he showed, na?
Sometimes some activities.
Yeah. So we had seen the cesium
Cobalt
and
16 he showed.
yeah, cobalt 60 activity, but we have not seen how the same peaks would look in a sodium iodide detector, right? So initially I start with that the exercise in sodium iodide detector. Then we have an exercise for you that, as sir discussed, we have got some samples from the International Atomic Energy Agency for the intercomparison exercise. This exercise is being held yearly. Every year they send us samples and we give them results, and only if our results are acceptable, only then we can say that our results are valid. So this is being held with 300 plus labs around the world. So we are happy to say that we have got all our results as acceptable, and and that has not been the case this year, but that has been the case from last 10 or 15 years. But for last 5 years I have been doing that, and we were able to get acceptable results in the last 5 years. But even before that, the same trend has been continuing. So we will also give you that sample, and we will show you how the format is, how the results come, how they give us samples, and how we have to analyze it. Okay. Initially we will see that how the spectrum for cobalt and cesium looks in a sodium iodide detector. So this exercise, what you are doing today, might take 2 days. Today you can take the efficiency and plot the efficiency graph. Tomorrow you can take the activity and calculate the activity of the sample. So since it's already 4 o'clock, right? So by 5:30 we can finish taking the efficiency values and plot it, and tomorrow we can take the readings for activity. So after this exercise, you will be more confident on analyzing this, analyzing any samples for in high purity germanium detector and also sodium iodide detector. Okay. So this is just a demonstration on how the cesium and cobalt peaks look in a sodium iodide detector. So I keep the samples inside.
You can do both this.
Yes. Let us see what happens if I put both the samples. What would be the conclusion? Yes. 3 peaks.
3 peaks.
Cobalt has 2 peaks.
Cesium or cobalt?
So let's start the counting. I hope you can see the peaks. How many peaks should we pick then?
Alienation peak is also there. Double escaping peak.
Some peaks.
Some peaks.
Some peaks should also be.
Some
So you can see that here we are getting the cesium peak.
Cesium.
at 661.
That is 511 kV.
661 kV.
Okay. And you are getting 1175 and 133. Yes. So we have both the peaks here, 1332. Okay, and some peak would appear somewhere over here at 2500. Yeah.
Coincidence.
Okay. Coincidence, yeah, that's a coincidence. And there is one more. Compton heads over here, you have two Compton heads and other peaks. So, can you see the difference between HPG and sodium iodide? The main difference over here is the channel difference. So, see there, when I get a cesium peak, the resolution was so good that I had used 658 to 663, around 5 keV of channels to get a proper peak, correct? Here you can see that my left marker is at what, 581, okay, and my right marker is at 742. So any peak that comes between that. So if there is a, let us say, if there is a radium source which gives bismuth at 609, that peak will not be detected if cesium is also present in this sample. Similarly, 795 peak of bismuth, and 795 you also get a cesium 134 peak. So if you have cesium 137 and 134, again that is not resolved properly in this peak. Again here you can see that cobalt peak was very wide in the HPG, that the two peaks were well resolved, correct? Here you can see that both the peaks are adjacent to each other. There is no much I think I cleared it. Not a problem. And it is not well resolved. So this is the basic difference between a sodium iodide and HPG. I hope this is clear. Right? Yeah. Any doubts here? No, it's actually there is an issue with this. This is not closing, so we are trying to close it. Once it closes, it should actually come a little bit down. So I'll stop the counting of the spectrum. We get more peaks than one. Yeah. So we get a spectrum of peaks. So now coming back to the topic. So can you give me what is it? The first one. No, not this. So during intercomparison exercise, we get an email or a printed, priorly we used to get a printed copy about a sheet like this which says IAEA TRC 2024 1 Worldwide Proficiency Test Exercise, Determination of Anthropogenic and Natural Radionuclides. So this year, the first page you will get the description of samples. So you can see there is a spiked water 1 and sample 1 and 2, and spiked water where sample 2 is quality control sample. 3, 4 are sediment samples. One is sediment and another is bauxite. And 5, 6, 7, 8 as discussed earlier are swipe samples. Sample number 5 is our sample that has to be analyzed. 6 and 7 are QC, 1 QC for cesium, 1 QC for strontium, and 8 is a blank sample. Okay, so this is the sample description, and we have to analyze. They have given the sample 2 concentration of values in sample 2. Here they have given concentration of sample radionuclides in sample 6 and 7, and they have asked us to how to handle these samples and choice of methods, and they have given us a deadline. Before this we have to submit. And the reference of for decay correction in all the samples is 1/1/2024, January 1, 2024. So that is what the reference date is. Now, how do we report it? So sample 1 has to be reported in becquerel per kg, and uranium and thorium, if we analyze by ICP-MS, we have to analyze. We have to report it in nanogram per gram. Okay, nanogram of uranium per 1 gram of sample. And then sample 3 is gamma ray emitting radionuclides. Sample 4 again gamma ray emitting radionuclides in becquerel per kg. Sample 5 we have to give it in becquerel per sample. So this is the units that they have given, and some more additional information. So if you get accepted, there is no good, better, best here. You have either accepted, not accepted, and warning. So you have to calculate. They will calculate precision and accuracy. If both precision and accuracy is accepted, your sample is accepted. If both are not accepted, your value is varying a lot. It is not accepted. Warning is when precision trueness rating is accepted, but precision is not accepted. Okay. Yeah, so that's it. So if this is clear, shall we analyze a sample? Okay. So you can all turn around to this detector over here. It will take 2 days. So 1 day for QC correction, 1 day for sample counting. So what to do? We have already have a spectrum. We will show you that. You can calculate, because this takes quite a long time for the spectrum to develop. So we have kept a sample over there. It has not even developed properly. So it will take time. Okay. So first I will give you the QC of water sample. Do you want to analyze water, or what are the samples that you have identified? Okay. Then I will give you the activity values for these radionuclides, and then you can continue in calculation of the area under the spectrum. I hope I am clear. First you identify the radionuclides that present in the spectrum, identify the radionuclides, then count the radionuclides, whatever the counts that you are getting, then calculate the efficiency. This much work you have to do today. So you can start. So keep a chair here so that nobody comes near this detector. You can take a chair from the lab. I just keep it here so that you can don't take this chair. So just you can all come closer. Start working on the piece. Take your chairs and come. So take your chairs.
We don't have to clear it.
No. So if you take background, your counting is done. Then you can go there.
Downside. End to tail.
They're asking questions. This second batch, sir. Identify material, radionuclide identification. Same, sir.
59 as well as
Same, sir. What is the first year code? Swipe, sir. Swipe all around the radionuclide.
21018.
as
you have to take that plus or minus also.
Okay, note it down here.
Plus or minus you have to take?
0.8.
Select it, okay. Next. And that, after the area, that also.
You note it down. Tomorrow they will talk about uncertainty calculation. At that time it will be useful. No, that is the starting point. Consider the starting point.
Six to develop here.